talk about implicit differentiation a little bit. Let's think of a new way to do it, because here's one like we had previously: 3x times e to the y minus 7x squared y cubed plus 4x minus 2 equals 0. That was one where we said that'd be a good candidate for, if we were looking for dy dx, slope of the tangent line, blah, 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 rate of change of y with respect to x. To do that, that's not going to be easy to come up with a y equals function of x, right? So we did this implicit differentiation method before. Let's think of it, though, we can actually come up with a new way of doing this one, a new way of doing implicit differentiation. Same idea, y, we are assuming here y is some function of x, but we can't explicitly define it. And so we're just going to implicitly do our differentiation. Backdoor kind of thing. Okay? Well, let's consider our left-hand side here. That's just a z function of xy, right? That, just think of it in terms of a z, okay? Well, then one note here is that z is f of xy, but also z is equal to 0. That'll be significant in just a second, okay? So we've got a function of xy. Okay. Now, we're looking for dy dx, right? We're looking for dy dx, but let's approach this. It'll come, dy dx will come out of this. But let's think of, let's get, z is our f of xy, so let's think of our dz dx. Or the partial, I guess, of z with respect to x. Okay. Well, using our knowledge here, using this chain rule, what would we have to do to get the partial of z with respect to x? Well, the path to x, since y, we've got y as a function of x, that's also something we've got. It's implicitly defined, but y is some function of x. So the path to x, here's z is xy, but y is also a function of x, isn't it? So I got to go through x here, but then also through y, okay? So it'd be the partial of z with respect to x times, well, this is just that, plus, then if I go through here, it'd be the partial of z with respect to y times dx, or dy dx. Oops. This should be dz dx. dz dx, okay. Now, here's where the fact that z equals 0 comes in. The derivative of z with respect to x, I'm not talking about the partial here, I put partial, but I meant just the derivative of z with respect to x, okay. The partial of z with respect to x, since z is 0, this derivative is 0. Derivative of 0 is 0, right? For anything. So I've got the partial of z with respect to x plus the partial of z with respect to y, dy dx. So this is how we're going to get dy dx, because here's dy dx, so let's solve that for dy dx. What would dy dx here equal? Well, you'd subtract the partial of z with respect to x and then divide off the partial of z with respect to y. So we subtract that and then divide by that. Okay? Or the way they the way they typically write in the book here is this is minus partial of f with respect to x over the partial of f with respect to y. Where this function, that's defining our function f. Yes, that's if you have this equal to 0. Yeah, that is important. Okay. They refer to this as equation 6, by the way, if they reference that. Okay, so here's what we've got. So let's go back to this one without writing it over. So we've got 3x e to the y. So my dy dx, instead of going through that implicit procedure we went through before, let's just use this. It's minus the partial with respect to x. Divide that by the partial with respect to y. So it's negative of what's the partial of this with respect to x. 3e to the y minus 14xy cubed plus 4. Derivative of that 0. Divide that by this partial with respect to y, so that would be 3x e to the y minus 21x squared y squared. That's it. Okay. So now that we know that's it. That's what you would get if you went through that. Remember, these were pretty long. If you recall back, that's your dy dx. Yeah, back when we did it, the early chapter we did it in, that took us quite a while. But now that we know about partial derivatives, not so much. A little easier. Yeah, the one thing to note is that you do need this stuff equal to 0. So if we've got this, y squared minus x squared equals sine of xy. I want to find dy dx. For that, to use the dy dx equals the negative partial derivative of f with respect to x partial f with respect to y, it does need one side to be 0. Yeah, if f of xy equals 0 is the way that works. So yeah, subtract the sine xy. Then we can do this dy dx equals, well, it'd be negative of what? Negative 2x minus cosine xy. Derivative of the inside would be what we're doing, partial with respect to x, so that'd be y. Over then the partial of f with respect to y. So that'd be 2y. That'd be 0. Minus cosine of xy again. But now the derivative of this with respect to y would just be x. So that would be, well, just be positive 2x plus y cosine of xy over 2y minus x cosine xy. Right. So again, that we may have done that one back when, but with the old method. But now it's really just two things with the partial derivatives. And the other thing, let me real quick hit this with you here. You can extend it to 3 variables. If you've got f of xyz equals 0, of course, then you've got what you're thinking there is you've got z in terms of like here. We've got x cubed. Here's an example. x cubed plus z squared plus y e to the xz plus z cosine of y equals 0. Okay. So you've got this long monstrosity, and it's not going to be easy to get z solved for, right? So what if I want to know the partial of z with respect to x? You know, we've done partials, but that's going to be hard to get z equals and to get it the way we've. So, yeah, what we do is we just say, well, this right here is our function f, and so that's going to be, turns out, very similar to the dy dx. It's negative the partial of x with respect of f with respect to x. Divide that by the partial of f with respect to z. Just like dy dx was the partial of f with respect to x over partial of f with respect to y. Yeah. And then partial of z with respect to y be negative. Yep. It's partial of f with respect to y over the partial of f with respect to z. Okay? All right.